Okay, so in the previous two videos, we saw how there are certain operations, certain indicators that a function is going to have some, let's say, some quirks or some breaks in its domain. In this problem, we saw breaks at positive and -2 for x. We saw that manifested in the graph with these asymptotes, right? Where the graph went shooting down like this and then coming up here. This red line is like an invisible fence that the function doesn't cross over. That was at -2, and there was another one here at +2. So that's why we had to exclude those values from the domain. In a radical, same thing, right? When we looked at the graph over here, we saw that it didn't go past this point because any x value past this point, if I plugged it in here, would give me a we showed the example of if I plugged in 10, this would be negative, right? So we have to stop it at a certain point. That's what we see with functions that have radicals and fractions. In a function like this, a function that looks like this has no fractions, therefore it can't be 0 in the denominator, and it has no square root symbol, so we don't have to worry about positives and negatives. So with a function like this, we see that it spans all the way from the left to the right. Now, obviously the window is, of a finite size, but we can assume there's no breaks. There's none of those invisible lines. It's continuous all the way from the left to the right. So for a function like this, we would say that the domain is all real numbers. And I talked about it in a previous video. The symbol for that sometimes looks like this, okay? But what we're going to use to express domain and range is this concept of interval notation. And interval notation looks like an ordered pair, but there are some different symbols that we use for this. So you start to see these infinities. When you write the interval notation for a domain or for a range, and we're going to look at some other things later on this, the number here that's on the left, this is the left, what we call the leftmost point. So for a function like this, okay, what we're looking at right now, the leftmost point of this graph, it's going down, right? The leftmost point, it's going to keep going and going and going and going and going. So its leftmost point is what we would call negative infinity. And that's as we're looking at the x scale, okay? And then we start where we end the interval wherever there's a break in the graph. So like as we trace, we don't see any breaks in this graph. There's none of those asymptotes. There's no holes. There's no stoppages. This is the rightmost point, okay, when there's no breaks. If there's a break in the graph, we'll talk about that when we need to, okay? But in interval notation, the first number we write is the leftmost point. The last number we write is the rightmost point. A couple of other things you'll need to remember about interval notation. We use parentheses with infinity all of the time, okay? Always, always, always parentheses. Always parentheses with infinity, okay? And I write my infinity as 2 small zeros because otherwise it'd look weird. That looks weird anyway, but you get the idea. Okay, so this is what interval notation for all real numbers looks like. When there's breaks in the domain, that's when things get weird. We're going to talk about that here in a second. Okay,